Picture this. You're lying in bed, staring at the ceiling, and your mind starts wandering. You think about dinosaurs, those massive creatures that once ruled our planet. But here's something that might surprise you. Those legendary reptiles were actually latecomers to Earth's story. Long before the first dinosaur ever took a breath, our planet was already teeming with life forms so bizarre and incredible that they'd make any science fiction movie look tame. Tonight, we're embarking on a journey that spans billions of years, diving deep into the forgotten chapters of Earth's history. We'll explore the rise and fall of entire worlds, witness mass extinctions that make modern disasters look like minor inconveniences, and meet creatures so strange that paleontologists are still scratching their heads trying to understand them. This isn't just about dusty fossils and academic theories. This is the epic tale of how life itself learned to survive, adapt, and conquer a hostile planet. What you're about to hear is the ultimate bedtime story for anyone fascinated by the mysteries of our ancient world. We'll travel through time periods with names like Cambrian, Ordovician, and Devonian, each one representing millions of years of evolutionary experimentation. You'll discover how simple single-celled organisms eventually gave birth to complex creatures with eyes, limbs, and the first primitive brains. We'll witness the planet's first mass extinctions, its ice ages, and the volcanic catastrophes that nearly wiped out all life forever. But here's what makes this story truly remarkable. Every single one of these ancient creatures, from the smallest trilobite to the most fearsome sea scorpion, played a crucial role in shaping the world that eventually welcomed dinosaurs. Without their struggles, their adaptations, and yes, even their extinctions, the age of dinosaurs never would have happened. They were the pioneers, the experimenters, the brave souls who figured out how to live, breathe, and thrive on a planet that seemed determined to kill them. So settle in, get comfortable, and prepare your mind for a journey unlike any other. We're about to explore 3 hours of the most incredible, most dramatic, and most important story ever told. The story of life before dinosaurs. Trust me, by the time we're finished, you'll never look at our planet the same way again. Let's begin this extraordinary adventure at the very beginning, when Earth itself was nothing more than cosmic dust swirling through the void of space. About 4.5 billion years ago, our solar system was a chaotic place. The sun had just formed from a massive cloud of gas and dust, and what remained was scattered throughout space in countless fragments. These weren't tiny specks. We're talking about chunks of rock and metal that could stretch for hundreds of kilometers. Day after day, these enormous pieces crashed into each other with unimaginable force, gradually sticking together through gravity and sheer momentum. Imagine the violence of those early collisions. Every impact released energy equivalent to millions of nuclear bombs, heating the growing planet to temperatures that would melt steel instantly. The early Earth was essentially a molten ball of rock floating through space, constantly bombarded by asteroids and comets. There were no oceans, no atmosphere as we know it, and certainly no life, just endless seas of lava, toxic gases, and radiation levels that would be instantly lethal to any modern organism. This hellish period lasted for nearly 1 billion years. That's longer than complex life has existed on Earth today. For perspective, If Earth's entire history were compressed into a single day, this violent formation period would last until about 5 in the morning. It's almost impossible to comprehend such vast stretches of time, but that's exactly what makes this story so incredible. Slowly, gradually, the bombardment began to decrease. The largest chunks of debris had either crashed into planets or been flung out of the solar system entirely. As the impacts became less frequent, something remarkable started to happen. The Earth began to cool. Water vapor that had been locked in the atmosphere as superheated steam finally condensed into liquid form. For the first time in our planet's history, rain began to fall. But this wasn't gentle spring rain. Picture torrential downpours that lasted for thousands of years, each drop hitting a surface hot enough to instantly vaporize it back into steam. This cycle continued for eons. Water falling, turning to vapor, condensing again, falling once more. Gradually, very gradually, the surface temperature dropped enough for liquid water to finally remain stable. By about 3.7 billion years ago, nearly a billion years after Earth's formation, our planet had transformed into something vaguely recognizable. The temperature had dropped to levels similar to what we experience today. The endless lava seas had cooled and solidified into rocky continents. Most importantly, vast oceans had formed, covering most of the planet's surface. Yet, even with these dramatic improvements, Earth was still a world that would seem utterly alien to us. The atmosphere contained almost no oxygen. Instead, it was dominated by carbon dioxide, methane, and other gases that would be toxic to most modern life forms. The sky probably had a strange, otherworldly color, perhaps orange or brown, rather than the blue we're familiar with. The only sounds would have been the constant crashing of waves against rocky shores and the occasional rumble of volcanic eruptions. The oceans themselves were unlike anything we know today. They were probably much warmer, possibly reaching temperatures of over 40 degrees Celsius in many areas. The water was filled with dissolved minerals and chemicals that had been leached from the rocks during those endless millennia of rain. It was a primordial soup of elements, waiting for the right combination of circumstances to spark something extraordinary. And then, in those dark, warm waters, something absolutely incredible happened. We don't know exactly when, and we certainly don't know exactly how, but somehow, somewhere in Earth's ancient oceans, the first living organisms appeared. These weren't anything like the complex creatures we see today. They were unimaginably simple, just single cells floating in the water, barely more complex than tiny bubbles of organized chemistry. These first life forms were so basic that they barely qualify as life by our standards. They had no eyes, no limbs, no brains, no way to move themselves through the water. All they could do was absorb nutrients from their surroundings and, when they had gathered enough energy, split themselves in two to create copies. It was reproduction at its most fundamental level, and it was the beginning of everything that would follow. For billions of years, billions, these simple organisms were the only life on Earth. They floated through the oceans, slowly evolving, gradually becoming more sophisticated. Some of them developed the ability to harness energy from sunlight. beginning the process of photosynthesis that would eventually transform our planet's entire atmosphere. Others learned to process different types of chemicals, creating the first primitive ecosystems. But perhaps most importantly, some of these early organisms began producing oxygen as a waste product. This might seem like a small detail, but it would prove to be one of the most significant developments in Earth's history. Oxygen was actually poisonous to most early life forms. It was their equivalent of toxic waste. But as these photosynthetic organisms multiplied over millions of years, they began pumping more and more oxygen into the atmosphere and oceans. This gradual increase in oxygen levels set the stage for everything that would follow. Without oxygen, complex life as we know it simply cannot exist. It's the fuel that powers our cells, the element that makes possible the intricate chemistry of advanced organisms. But it would take nearly 3 billion years of slow, patient evolution before oxygen levels reached the point where more complex life could finally emerge. During this incredibly long period, Earth experienced numerous dramatic changes. Continents formed and broke apart. Ice ages came and went. Asteroid impacts periodically disrupted the slow progress of evolution. Volcanic eruptions released massive amounts of gases into the atmosphere, temporarily altering the planet's climate. Through it all, those simple single-celled organisms persisted, adapted, and gradually became more sophisticated. By about 1 billion years ago, some of these cells had learned to work together, forming the first multicellular organisms. These were still incredibly simple by modern standards, basically just clusters of cells that had decided cooperation was more effective than going it alone. But this development opened up entirely new possibilities for evolution. The stage was finally set for the next great chapter in Earth's history. Oxygen levels had risen to the point where more complex life could survive. The oceans had stabilized into environments that could support diverse ecosystems. The climate had settled into patterns that would persist for millions of years at a time. All the pieces were in place for life to finally explode into the incredible diversity of forms that would define the next phase of our planet's story. What happened next was so dramatic, so sudden in geological terms, that scientists have given it a special name, the Cambrian explosion. This event, which began about 538 million years ago, represents the most rapid diversification of life in Earth's history. In the span of just a few million years, virtually all the major groups of animals that exist today first appeared in the fossil record. Before the Cambrian period, Earth's land masses had been joined together in a massive supercontinent called Rodinia. But as the Cambrian began, this ancient continent started breaking apart, splitting into smaller land masses that drifted across the globe. The largest of these new continents was called Gondwana, and it dominated the southern hemisphere of our planet. But the real excitement was happening in the oceans. For the first time in Earth's history, animals were developing hard shells, complex eyes, jointed limbs, and sophisticated nervous systems. The simple, soft-bodied creatures that had dominated the seas for billions of years suddenly found themselves sharing their environment with an incredible array of new, more advanced life forms. The Cambrian explosion wasn't actually an explosion in the literal sense. It unfolded over tens of millions of years. But compared to the incredibly slow pace of evolution that had characterized the previous billions of years, it might as well have been instantaneous. Scientists are still debating exactly what triggered this remarkable burst of evolutionary creativity. But most agree that rising oxygen levels played a crucial role. Remember those simple organisms that had been producing oxygen as waste for billions of years? By the Cambrian period, they had finally succeeded in transforming Earth's atmosphere and oceans. Oxygen levels had reached the point where more complex life forms could finally thrive. These new organisms could use oxygen to power much more sophisticated cellular processes, enabling them to grow larger, move faster, and develop more complex body structures. The average temperature during the Cambrian was much warmer than today, probably around 43 degrees Celsius in many ocean areas. Combined with higher levels of both oxygen and carbon dioxide, these conditions created the perfect environment for evolutionary experimentation. Life forms began developing features that had never existed before. Eyes capable of detecting light and movement, limbs that could propel them through the water, mouths that could capture and process food, and protective shells that could defend against predators. One of the most successful groups to emerge during this period was the trilobites. These arthropods, with their distinctive segmented bodies and hard exoskeletons, suddenly appeared throughout the world's oceans. They came in an incredible variety of shapes and sizes, from tiny scavengers that fed on organic debris to larger predators that actively hunted other animals. Some had enormous compound eyes that could detect the slightest movement in the water, while others were completely blind, relying on other senses to navigate their underwater world. Trilobites were so successful that they would dominate marine ecosystems for hundreds of millions of years. In fact, they're one of the most abundant fossils we find today, testament to their incredible success during this ancient period. They developed sophisticated methods of feeding, reproducing, and defending themselves that allowed them to thrive in virtually every marine environment on Earth. But trilobites weren't the only remarkable creatures to emerge during the Cambrian. The first true fish also appeared during this period, though they were unlike any fish we know today. These early vertebrates were slimy, jawless creatures that resembled modern eels more than typical fish. They had primitive spinal cords, but lacked many of the features we associate with advanced vertebrates. No jaws, no paired fins, no sophisticated sensory organs. One of these early fish-like creatures was called Uninozoon, a strange worm-like animal that possessed what might have been the first primitive backbone. It didn't have true bones as we understand them, but it had developed a flexible rod of cartilage that provided structural support for its body. This innovation would prove to be one of the most important developments in the history of life on Earth. The Cambrian seas were also home to some truly bizarre creatures that looked like nothing we see today. Take Opabinia, for example, a deep-sea predator that appeared to have been designed by someone with a very strange sense of humor. This creature had 5 mushroom-shaped eyes arranged on top of its head and a long, flexible proboscis, ending in a claw-like appendage that it used to capture prey. It would use this bizarre trunk to snatch up small animals and deliver them directly to its mouth, located on the underside of its body. As these new life forms proliferated, they began to establish the first complex predator-prey relationships in Earth's history. For billions of years, life had been relatively peaceful. Simple organisms floating around, absorbing nutrients, and occasionally bumping into each other. But now, for the first time, some creatures were actively hunting others for food. The most fearsome predator of the Cambrian seas was Anomalocaris, whose name means strange shrimp. Despite its name, this creature was actually more closely related to modern arthropods than to any type of shrimp. At just over 30 centimeters long, it was enormous by Cambrian standards, a true giant in a world of mostly small creatures. Anomalocaris was perfectly designed for hunting. It had large, sophisticated eyes that could track prey through the water, powerful swimming appendages that allowed it to move with surprising speed, and grasping arms that could capture and manipulate its victims. It roamed the ancient oceans like an underwater predator, feeding primarily on soft-bodied creatures like worms and early mollusks. The presence of such an effective predator forced other creatures to evolve new defensive strategies. Some developed harder shells, others learned to burrow into the seafloor, and still others evolved better sensory systems that could detect approaching danger. This evolutionary arms race between predators and prey would become one of the driving forces behind the incredible diversity of life that characterized the Cambrian period. However, just as life seemed to be flourishing and diversifying at an unprecedented rate, disaster struck. About 485 million years ago, a series of massive volcanic eruptions triggered one of Earth's first great mass extinction events. We still don't fully understand what caused this catastrophe, but its effects were devastating. The eruptions released enormous amounts of toxic gases into the atmosphere and oceans, poisoning many of the creatures that had evolved during the Cambrian explosion. Ocean temperatures fluctuated wildly, and the chemistry of seawater changed dramatically. Many of the bizarre experimental life forms that had made the Cambrian so remarkable simply couldn't adapt to these new conditions. The extinction wasn't total. Hardy survivors like the trilobites managed to weather the crisis and would continue to thrive for millions of years to come. But the event marked the end of the Cambrian period and the beginning of a new chapter in Earth's history. The age of initial experimentation was over, and life would now face the challenge of surviving in an increasingly complex and dangerous world. The Ordovician period that followed would bring its own remarkable developments, including the rise of even more fearsome predators and the first tentative steps of life onto dry land. But that's a story for our next chapter in this incredible journey through Earth's ancient history. The Ordovician period that followed the Cambrian extinction was like Earth hitting the reset button, and then discovering it had unlocked a whole new level of the game. Starting around 485 million years ago, our planet was about to witness something scientists call the Great Ordovician Biodiversification Event. If the Cambrian explosion was impressive, this was life saying, "Hold my beer," and proceeding to absolutely blow everyone's minds. Picture the scene. The continents were still drifting around like massive puzzle pieces, trying to find their proper places. Sea levels were dropping in some areas while rising in others, creating entirely new environments for life to explore. But here's the kicker. Oxygen levels in the oceans were climbing again, and this time they were reaching heights that would make even the most ambitious life forms start dreaming big. The moving continents were creating something that hadn't existed before. Isolated islands and separated marine environments. Think of it like nature's own laboratory, where different groups of organisms could evolve in isolation, developing unique characteristics without interference from their relatives elsewhere. These separated habitats were like evolutionary pressure cookers, each one producing its own special brand of weird and wonderful creatures. Fish were starting to look more like, well, actual fish. They were still a far cry from the streamlined swimmers we know today, but they were definitely making progress. The jawless, eel-like creatures of the Cambrian were slowly giving way to more sophisticated forms with better sensory systems and more efficient body designs. Evolution was learning the art of fine-tuning, taking the basic vertebrate blueprint and making incremental improvements. But if you thought the Cambrian had produced some scary predators, the Ordovician was about to introduce you to creatures that would make Anomalocaris look like a harmless goldfish. Enter the Eurypterids, commonly known as sea scorpions, though they weren't actually scorpions at all. These were arthropods that had decided to take the whole apex predator thing to an entirely new level. The first of these magnificent terrors was called Pentacopterus, and it could grow to over 1.5 meters in length. Imagine encountering this thing in the ancient seas, a creature the size of a large person, equipped with powerful claws, a segmented tail ending in a dangerous spike, and the kind of predatory instincts that would make a modern shark nervous. These weren't just big bugs, they were sophisticated hunting machines that had evolved specifically to dominate their marine environment. Sea scorpions had perfected the art of being terrifying. They possessed excellent vision, powerful swimming appendages, and crushing claws that could crack through the shells of their prey with ease. They were the submarines of the ancient world, patrolling the sea floor and striking fear into the hearts of every other creature unlucky enough to cross their path. But even these fearsome predators weren't the biggest bullies in the Ordovician playground. That distinction belonged to a group of creatures called nautiloids, specifically the massive Camarasaurus. These were ancient relatives of modern octopuses and squids, but they were built on a completely different scale. Picture a giant squid, but instead of being soft-bodied, it's protected by a massive shell and can grow up to 7 meters in length. Camarasaurs were the ultimate ocean overlords. They possessed sharp, powerful beaks that could slice through the toughest exoskeletons, tentacles that could grab and manipulate prey with incredible dexterity, and shells that provided protection from anything brave enough to fight back. They cruised through the ancient seas like living battleships, hunting down sea scorpions and other large predators as if they were appetizers at an underwater buffet. The relationship between these massive predators created some of the first truly complex marine ecosystems in Earth's history. Sea scorpions would hunt smaller creatures, but they themselves had to constantly watch out for the even more dangerous nautiloids lurking in the deeper waters. It was like a deadly game of underwater tag, where being it meant becoming someone else's lunch. Meanwhile, something equally revolutionary was happening in the shallow waters and along the coastlines. Plants, which had existed as simple algae in the oceans for millions of years, were finally making their first tentative steps onto dry land. This might not sound like a big deal, but it was actually one of the most significant developments in the history of life on Earth. These early land plants weren't the towering trees or colorful flowers we're familiar with today. They were more like primitive mosses, simple green organisms that had no roots, no stems, and no specialized structures for dealing with life outside of water. They could only survive in areas where there was constant moisture, clinging to rocks near streams and lakes, where they could absorb water directly through their surfaces. Despite their humble appearance, these pioneering plants were absolute game changers. For the first time in Earth's history, something was living permanently on dry land. They began the slow process of transforming the planet's atmosphere by absorbing carbon dioxide and releasing oxygen, gradually making the air more suitable for other forms of life to eventually follow. But plants weren't content to remain simple forever. As the Ordovician period progressed, they began developing more sophisticated structures. Some evolved primitive stems that could transport water more efficiently, while others developed simple root-like structures that could anchor them to the ground and help them absorb nutrients from the soil. The presence of these early plants began to change the very nature of the continents. Previously, the land had been nothing but bare rock, sand, and gravel. Now, for the first time, there were patches of green life scattered across the landscape. It was the beginning of what would eventually become the vast forests and grasslands that would cover much of our planet. However, all this progress was about to face a serious challenge. Around 460 million years ago, Earth began experiencing one of its most severe ice ages. This wasn't just a temporary cold snap. This was a full-scale glacial period that would last for millions of years and fundamentally alter the planet's climate and geography. The Ice Age began in what is now the southern hemisphere, where massive glaciers started forming and spreading across the continents. As more and more of the planet's water became locked up in ice, sea levels dropped dramatically. Ocean temperatures plummeted, and the warm, tropical conditions that had characterized the early Ordovician gave way to a much harsher, more challenging environment. Marine life, which had been thriving in the warm, oxygen-rich seas, suddenly found itself struggling to survive in a world of cold water and reduced living space. The drop in sea level meant that many of the shallow marine environments where life had been most diverse simply disappeared, forcing creatures to adapt to deeper, colder waters or face extinction. The Ice Age hit marine animals particularly hard. The giant nautiloids, which had been the undisputed rulers of the oceans, found their populations severely reduced. Many species of sea scorpions went extinct entirely, unable to adapt to the new conditions. Even the hardy trilobites, which had survived the end Cambrian extinction, saw their numbers drop dramatically. Some scientists believe that this ice age was actually triggered by the success of those early land plants. As plants spread across the continents, they began absorbing massive amounts of carbon dioxide from the atmosphere. Carbon dioxide is a greenhouse gas that helps trap heat in the atmosphere. So removing it caused global temperatures to drop. In a sense, the plants had accidentally triggered their own ice age by being too successful at photosynthesis. By the time the ice age reached its peak, around 443 million years ago, an estimated 80% of all marine species had gone extinct. It was a catastrophe that made the end Cambrian extinction look minor by comparison. The diverse, thriving ecosystems that had developed during the early Ordovician were reduced to a handful of hardy survivors clinging to life in a frozen world. But here's the thing about life. It's incredibly resilient. Even in the face of such devastating challenges, some creatures manage to survive and even thrive. The trilobites, though reduced in number, continued to evolve and adapt. Some fish species weathered the crisis and emerged stronger than before. And perhaps most importantly, those pioneering land plants had established a foothold on the continents that would prove impossible to dislodge. The Ordovician period officially ended around 443 million years ago, but its legacy lived on in the creatures that had survived the Great Ice Age. These hardy survivors would become the foundation for the next chapter in Earth's history, a period that would see life not only recover from the devastating extinction, but explode into even greater diversity than before. The Silurian period that followed would witness the melting of the great ice sheets, the return of warm seas, and the rise of new predators even more fearsome than their Ordovician predecessors. Life was about to enter a new phase of experimentation and expansion, one that would push the boundaries of what was possible in ways that would have seemed impossible just a few million years earlier. As the ice began to melt and sea levels started to rise again, the stage was set for one of the most remarkable recovery stories in the history of life on Earth. The creatures that had survived the Ordovician extinction were about to inherit a world full of new opportunities, and they were going to make the most of them in spectacular fashion. The Silurian period began around 419 million years ago, with what could only be described as a massive planetary thaw. The ice sheets that had dominated the southern hemisphere for millions of years finally began to retreat, releasing enormous amounts of water back into the oceans. Sea levels rose dramatically, creating vast new shallow marine environments perfect for life to recolonize and diversify. The climate stabilized into something much more hospitable than the harsh conditions of the late Ordovician. Warm tropical seas spread across much of the planet, providing ideal conditions for the survivors of the Great Extinction to not only recover, but flourish in ways that would have been impossible during the Ice Age. With the disappearance of many of the large predators that had dominated the Ordovician seas, new opportunities opened up for the creatures that had managed to survive. The nautiloids, though reduced in number, began to diversify and evolve into new forms. Some developed more streamlined shells for faster swimming, while others grew even larger and more fearsome than their predecessors. But the real stars of the Silurian recovery were the sea scorpions, which not only survived the extinction, but came back stronger than ever. With many of their competitors eliminated, these arthropod predators had the opportunity to evolve into forms that were truly spectacular. Carcinosoma, one of the largest sea scorpions ever discovered, grew to over 2 meters in length, making it one of the most formidable predators in the ancient seas. These massive sea scorpions were perfectly adapted for their role as apex predators. They possessed powerful claws that could crush shells, sophisticated sensory organs that could detect prey from great distances, and swimming appendages that allowed them to move through the water with surprising speed and agility. They were like underwater tanks, armored, armed, and absolutely deadly. Fish continued their slow but steady evolution during the Silurian. One of the most significant developments was the appearance of the first fish with movable jaws. This might seem like a minor improvement, but it was actually revolutionary. Jawed fish could actively hunt and process food in ways that their jawless predecessors never could. They could grab, bite, and chew, opening up entirely new feeding strategies and ecological niches. The Silurian seas also witnessed the emergence of the first coral reefs, though these weren't quite like the colorful tropical reefs we know today. These ancient reefs were built by different types of organisms, including various types of marine invertebrates that had learned to work together to create complex three-dimensional structures on the seafloor. These early reefs became centers of marine biodiversity, providing shelter and feeding opportunities for countless species. They were like underwater cities, bustling with activity as different creatures carved out their own niches within the reef ecosystem. Trilobites scuttled across the reef surfaces. Small fish darted between the coral-like structures, and various types of marine invertebrates filtered nutrients from the water. But perhaps the most significant development of the Silurian period was happening not in the oceans, but on the continents. The land plants that had first appeared during the Ordovician were becoming more sophisticated and beginning to spread across the landscape in ways that would fundamentally alter the planet's environment. These Silurian plants were developing features that would allow them to thrive in terrestrial environments. They evolved the first true stems, which could transport water and nutrients more efficiently throughout the plant. They developed simple root systems that could anchor them to the ground and extract nutrients from the soil. Most importantly, they began to develop waxy coatings that could prevent water loss, allowing them to survive in areas that were much drier than the moisture-rich environments their ancestors had required. As plants spread across the continents, they began to transform the very nature of the land itself. Their roots broke down rocks, creating the first primitive soils. Their photosynthesis continued to pump oxygen into the atmosphere while removing carbon dioxide, gradually making the air more suitable for other forms of life. The increasing oxygen levels had a profound effect on the planet's chemistry and climate. Unlike the previous ice age, which had been triggered by plants removing too much carbon dioxide, this time the balance was more stable. The combination of increased oxygen and moderate carbon dioxide levels created conditions that were ideal for life to expand and diversify. It was during this period that the first arthropods began to make serious attempts at leaving the oceans and colonizing the land. These early terrestrial pioneers were probably relatives of modern centipedes, millipedes, and arachnids. They were small, simple creatures that initially may have only ventured onto land to escape predators or search for new sources of food. The transition from water to land was incredibly challenging. These early land-dwelling arthropods had to solve problems that no creature had ever faced before. They needed to develop new ways to breathe air instead of extracting oxygen from water. They had to figure out how to prevent their bodies from drying out in the harsh terrestrial environment. They needed to learn how to move effectively on solid ground rather than swimming through water. Many of these early land colonizers still maintained strong connections to aquatic environments. Silurian scorpions, for example, had gills that needed to be kept moist to function properly. They could venture onto land for short periods, but they had to return to water regularly to survive. They were essentially amphibious, living in both worlds, but not fully adapted to either. Despite these limitations, the colonization of land represented a breakthrough that would have profound implications for the future of life on Earth. For the first time in our planet's history, complex organisms were learning to exploit the vast resources of the terrestrial environment. The continents, which had been sterile wastelands for billions of years, were finally becoming home to living creatures. The Silurian period came to an end around 419 million years ago, but not with the dramatic extinction events that had characterized the conclusions of previous periods. Instead, it ended with a series of relatively minor climate changes that gradually shifted the planet's environment toward the conditions that would characterize the next great chapter in Earth's history. The stage was now set for what would become known as the Devonian period, often called the Age of Fishes. This would be a time when vertebrates would finally begin to realize their full potential, when the first forests would spread across the continents, and when life would face both incredible opportunities and devastating challenges that would reshape the biological landscape of our planet forever. The Devonian period burst onto the scene around 419 million years ago, like nature's own renaissance, a time when life decided to throw caution to the wind and experiment with designs that would make even the most creative minds jealous. This wasn't just another geological period. This was the moment when Earth's oceans became a showcase for some of the most incredible predators our planet has ever seen. The early Devonian seas were dominated by creatures that would make modern great white sharks look like minnows. While the first primitive sharks were indeed evolving during this time, they were far from being the ocean's top predators. That honor belonged to a group of heavily armored fish called placoderms, and among them was a monster that paleontologists have named Dunkleosteus. Picture this, a fish the size of a city bus, but instead of teeth, it had massive bony plates that functioned like living guillotines. Dunkleosteus could grow up to 10 meters in length, making it one of the largest predators that has ever lived. Its jaw was so powerful that scientists estimate it could bite with a force of over 11,000 pounds per square inch. That's more than twice the bite force of a saltwater crocodile, which currently holds the record for the strongest bite of any living animal. The head of Dunkleosteus was essentially a living battering ram, armored with thick, bony plates that could withstand attacks from other predators. Its eyes were positioned perfectly for hunting, and its streamlined body design allowed it to move through the water with surprising speed for such a massive creature. When Dunkleosteus opened its mouth, those razor-sharp, bony plates would slice through its prey like a pair of enormous scissors, capable of cutting through virtually any armor or shell that other creatures had evolved for protection. But Dunkleosteus wasn't just big and scary, it was also incredibly sophisticated. Recent studies of its fossils have revealed that it had a complex nervous system and advanced sensory organs that would have made it an incredibly effective hunter. It could detect the slightest movements in the water, track prey over long distances, and coordinate complex attacks that would have been impossible for simpler predators. The presence of such a formidable predator had profound effects on the evolution of other marine creatures. Fish began developing new defensive strategies, from harder scales to more sophisticated schooling behaviors. Some species evolved to become faster swimmers, while others developed better camouflage or learned to hide in places where the massive Dunkleosteus couldn't reach them. While the oceans were being dominated by these incredible predators, something equally revolutionary was happening on land. The simple plants that had begun colonizing the continents during the Silurian were undergoing their own dramatic transformation. For the first time in Earth's history, true trees were beginning to appear. These weren't the towering giants we might imagine when we think of ancient forests. The earliest trees were relatively small, perhaps only a few meters tall, but they represented a quantum leap in plant evolution. They had developed complex root systems that could anchor them firmly to the ground and extract nutrients from deep within the soil. They had sophisticated vascular systems that could transport water and nutrients throughout their bodies, even to the very tops of their branches. Most importantly, these early trees had figured out how to grow tall. Height was the key to success in the plant world because it meant access to sunlight. The taller a plant could grow, the more light it could capture, and the more energy it could produce through photosynthesis. This led to an evolutionary arms race among plants, with different species competing to grow taller than their neighbors. As these primitive forests spread across the continents, they began to transform the entire planet's atmosphere. Trees were incredibly efficient at photosynthesis, absorbing massive amounts of carbon dioxide from the air and releasing oxygen as a byproduct. The oxygen levels in Earth's atmosphere began to rise dramatically, creating conditions that would prove crucial for the next stage of animal evolution. The increasing oxygen levels had a particularly profound effect on the arthropods that had begun colonizing the land during the Silurian. With more oxygen available, these creatures could grow larger and more active than ever before. Some developed into the first truly terrestrial arachnids, while others evolved into primitive insects that would eventually learn to fly. But the most significant development was happening in the shallow waters at the edges of the continents. Some fish species had begun spending more and more time in these marginal environments, areas where the water was so shallow that they frequently found themselves exposed to air. These fish were facing a challenge that would either kill them or force them to evolve in entirely new directions. The solution came in the form of primitive lungs. Some fish began developing air-breathing organs that could extract oxygen directly from the atmosphere. This was a revolutionary adaptation that would prove to be one of the most important developments in the history of vertebrate evolution. These early air-breathing fish were the ancestors of all land-dwelling vertebrates, including eventually dinosaurs, mammals, and humans. One of the most famous of these transitional creatures was Tiktaalik, a remarkable animal that possessed characteristics of both fish and amphibians. Tiktaalik had fins that were beginning to resemble primitive legs, complete with wrist-like joints that could support its weight on solid ground. It had a flattened head with eyes positioned on top, perfect for looking around while partially submerged in shallow water. Most importantly, it had both gills for breathing underwater and primitive lungs for breathing air. Tiktaalik represents one of the most important transitional forms in the fossil record, a creature that was perfectly adapted for life at the boundary between water and land. It could swim through deeper waters when necessary, but it could also use its powerful fins to push itself onto muddy shores or through very shallow streams. It was a bridge between two worlds, neither fully aquatic nor fully terrestrial, but perfectly suited for the marginal environments where the next great evolutionary breakthrough would occur. Following closely behind Tiktaalik came the first true tetrapods, four-legged vertebrates that represented the next step in the transition from water to land. These early tetrapods, creatures like Acanthostega and Ichthyostega, had developed true limbs with distinct fingers and toes, though they were still primarily aquatic animals that used their legs for swimming and maneuvering in shallow water rather than for walking on land. The development of limbs was a game-changing innovation that would eventually lead to the incredible diversity of land-dwelling vertebrates we see today. But in the Devonian, these early tetrapods were still experimental creatures trying to figure out how to make the most of their new anatomical features. Meanwhile, the arthropods that had colonized the land were diversifying rapidly. The first wingless insects appeared during this period, along with the ancestors of modern spiders and other arachnids. These terrestrial arthropods were pioneers, exploring ecological niches that had never been occupied before. They were learning to feed on the growing plants, to hunt each other, and to exploit the vast resources of the terrestrial environment. The Devonian forests were becoming complex ecosystems in their own right. Dead plant material was accumulating on the forest floor, creating rich soils that supported even more plant growth. The roots of trees were breaking down rocks and creating new types of soil chemistry. For the first time in Earth's history, the continents were becoming green, living landscapes rather than barren wastelands. But all this progress was about to face a serious challenge. As the Devonian period progressed, the very success of land plants began to create problems for marine life. The extensive root systems of the new forests were incredibly effective at breaking down rocks and extracting nutrients from the soil. This was great for the plants, but it created an unexpected consequence for the oceans. The nutrients that were being leached from the continents by plant roots were being washed into rivers and eventually carried out to sea. This massive influx of nutrients caused explosive growth of marine algae, creating what scientists call algal blooms on a planetary scale. These blooms were so extensive that they began to consume enormous amounts of oxygen from the seawater. The result was a gradual but devastating decrease in oxygen levels throughout the world's oceans. Marine creatures that had thrived in the oxygen-rich waters of the early Devonian suddenly found themselves struggling to survive in an environment that was becoming increasingly hostile to complex life. The effects of this oxygen depletion were catastrophic for marine ecosystems. The mighty Dunkleosteus, which had ruled the seas for millions of years, finally met its match. These massive predators required enormous amounts of oxygen to fuel their powerful bodies, and as oxygen levels dropped, they simply couldn't survive. One by one, the great placoderms disappeared from the fossil record, victims of an environmental disaster that they couldn't have possibly understood or prepared for. Trilobites, those incredibly successful arthropods that had survived multiple mass extinctions, also found themselves in serious trouble. Many species went extinct during this period, and those that survived were reduced to small, marginal populations. The diverse, thriving marine ecosystems that had characterized the early Devonian were collapsing as oxygen levels continued to drop. Sea scorpions, which had been such successful predators during the Silurian, also suffered massive population declines. Many species disappeared entirely, and those that survived were much smaller and less diverse than their predecessors. The age of giant marine arthropods was coming to an end, brought down not by competition or predation, but by changes in ocean chemistry that were beyond their control. By the end of the Devonian period, around 359 million years ago, marine life had been devastated. An estimated 70% of all marine species had gone extinct, making this one of the most severe mass extinction events in Earth's history. The diverse, complex marine ecosystems that had taken millions of years to develop were reduced to a handful of hardy survivors. Ironically, while marine life was suffering through this catastrophe, life on land was flourishing like never before. The forests continued to spread and diversify, creating increasingly complex terrestrial ecosystems. The first amphibians were making their tentative steps onto dry land, beginning the long process of vertebrate colonization of the continents. The Devonian extinction marked the end of an era in Earth's history. The age of giant marine predators was over, but the age of terrestrial life was just beginning. The stage was set for the next great chapter in our planet's story, a period when life would finally break free from its dependence on aquatic environments and begin to explore the vast possibilities of existence on dry land. The Carboniferous period that followed would see the development of the first great forests, the evolution of the first reptiles, and the beginning of the complex terrestrial ecosystems that would eventually give rise to the age of dinosaurs. But that transformation would come with its own challenges and catastrophes, as life continued its never-ending struggle to adapt and survive in an ever-changing world. The Carboniferous period exploded onto the scene around 359 million years ago, like nature's own green revolution, a time when plants decided to take over the world and succeeded beyond anyone's wildest imagination. If you thought the Devonian forests were impressive, the Carboniferous was about to show you what Earth looked like when plants really got serious about dominating the landscape. Picture a world where vast swamps and forests stretched from horizon to horizon, where the air was so thick with oxygen that a single spark could ignite massive wildfires, and where arthropods grew to sizes that would make modern horror movies look like children's cartoons. This was the Carboniferous, a period when life on land reached levels of abundance and diversity that were absolutely staggering. The forests of the Carboniferous weren't just bigger than their Devonian predecessors, they were fundamentally different. These were the first truly massive tree ecosystems, with some specimens reaching heights of over 40 meters. Imagine walking through a forest where the canopy disappeared into misty heights above your head, where the trunks of ancient trees were so wide that it would take dozens of people holding hands to encircle them. These weren't the familiar hardwood forests we know today. The Carboniferous forests were dominated by primitive tree-like plants with names like lepidodendron and sigillaria, massive, scale-covered giants that looked more like something from an alien planet than anything in our modern world. Their trunks were covered in diamond-shaped scars where old leaves had fallen off, giving them a distinctive armored appearance that would have made them instantly recognizable even from a great distance. The root systems of these ancient giants were equally impressive. They spread out through the swampy soils like vast underground networks, breaking down rocks and extracting nutrients with incredible efficiency. The forests were so dense and productive that dead plant material was accumulating faster than it could decay, creating thick layers of organic matter that would eventually become the coal deposits we mine today. But here's where things get really interesting. All this plant growth was pumping oxygen into the atmosphere at unprecedented rates. During the Carboniferous, oxygen levels rose to about 35% of the atmosphere, compared to the 21% we have today. This might not sound like a huge difference, but it had absolutely profound effects on animal life. Remember those arthropods that had first colonized the land during the Silurian and Devonian? Well, with all this extra oxygen available, they were about to embark on an evolutionary experiment that would produce some of the most incredible creatures our planet has ever seen. Arthropods obtain oxygen through small openings in their bodies called spiracles. And with so much oxygen available, they could grow to absolutely enormous sizes. The star of this incredible size explosion was a millipede called Arthropleura. And when I say it was big, I mean it was absolutely massive. This creature could grow to over 2.5 meters in length. That's longer than most cars. Imagine encountering this giant arthropod crawling through a carboniferous forest, its segmented body undulating through the undergrowth like some kind of prehistoric train. Fortunately, for any time travelers who might have found themselves in a carboniferous forest, Arthropleura was a vegetarian. Despite its intimidating size, it fed exclusively on the abundant plant material that littered the forest floor. It was essentially a living garbage disposal, processing enormous amounts of dead leaves and plant debris and helping to keep the forest ecosystem functioning smoothly. But Arthropleura wasn't the only giant arthropod roaming the carboniferous landscape. The skies were dominated by enormous flying insects that would make modern dragonflies look like tiny gnats. Meganura, one of the largest flying insects that ever lived, had a wingspan of over 75 centimeters. That's about the size of a large bird of prey. These giant dragonflies were formidable predators, capable of snatching smaller insects right out of the air with their powerful mandibles. They had enormous compound eyes that could track prey across great distances, and their flight capabilities were so advanced that they could hover, dart, and maneuver with incredible precision. The carboniferous skies were like an aerial battlefield, with these massive insects engaging in dogfights that would have been spectacular to witness. The success of these giant arthropods was directly linked to the high oxygen levels of the carboniferous atmosphere. Their respiratory systems were perfectly adapted to take advantage of the oxygen-rich environment, allowing them to grow to sizes that would be impossible in today's atmosphere. They were living proof of just how dramatically environmental changes could affect the evolution of life on Earth. While arthropods were ruling the land and air, vertebrates were also making significant progress in their conquest of terrestrial environments. The first true amphibians were becoming increasingly sophisticated, developing better adaptations for life on land while still maintaining their connection to aquatic environments for reproduction. One of the most remarkable amphibians of the Carboniferous was Diplocaulus, a creature that looked like it had been designed by someone with a very unusual sense of aesthetics. This strange animal had a distinctive boomerang-shaped head that made it instantly recognizable among Carboniferous fauna. Scientists believe this bizarre head shape may have helped it glide through the water more efficiently, or perhaps served as a defensive mechanism against predators. Diplocaulus was about 90 centimeters long and spent most of its time in the abundant swamps and rivers of the Carboniferous landscape. Its flattened body and powerful tail made it an excellent swimmer, while its unusual head shape gave it a hydrodynamic advantage that helped it capture prey and avoid becoming prey itself. But the most significant development in vertebrate evolution during the Carboniferous was happening with a group of amphibians that were beginning to solve one of the biggest challenges facing life on land: reproduction. Up until this point, even the most terrestrial vertebrates had to return to water to lay their eggs. The eggs were soft and vulnerable, requiring the moist environment of ponds or streams to develop properly. Then, in one of the most important evolutionary breakthroughs in Earth's history, some amphibians developed the ability to lay eggs with hard shells. These amniotic eggs contained all the nutrients and moisture that a developing embryo needed, protected by a tough shell that could survive in terrestrial environments. For the first time in Earth's history, vertebrates could reproduce entirely on land. This development gave rise to the first amniotes, the ancestors of all modern reptiles, birds, and mammals. These early amniotes were small, lizard-like creatures that looked quite unremarkable, but they carried within their genes the potential for all the incredible diversity of land-dwelling vertebrates that would follow. The ability to lay shelled eggs was like giving vertebrates a passport to explore every corner of the terrestrial world. They were no longer tied to bodies of water for reproduction, which meant they could colonize environments that had previously been inaccessible. Deserts, mountains, forests, all of these habitats became potential homes for amniotic vertebrates. But just as life on land was reaching these incredible new heights of diversity and abundance, the planet was about to undergo another massive transformation. The continents, which had been slowly drifting across the globe for millions of years, were beginning to come together in a way that would fundamentally alter Earth's geography and climate. Around 335 million years ago, the various land masses that had been scattered across the planet began to collide and merge, forming a massive supercontinent that geologists call Pangaea. This wasn't just a minor rearrangement of the continents. It was a complete reorganization of the planet's surface that would have profound effects on both climate and life. The formation of Pangaea had immediate and devastating consequences for the lush forests that had characterized the Carboniferous period. The vast tropical swamps that had covered much of the planet suddenly found themselves in new climatic conditions as the continents moved into different positions relative to the equator and the poles. Many of the great forests that had been thriving in coastal areas suddenly found themselves hundreds of kilometers inland, cut off from the moisture sources that had sustained them for millions of years. The climate became increasingly arid as the supercontinent formed, and the once lush landscapes began to dry up and transform into deserts. The effects on oxygen levels were dramatic and immediate. As the great forests died back, the amount of oxygen being pumped into the atmosphere dropped significantly. The oxygen-rich environment that had enabled giant arthropods to thrive suddenly became much less hospitable to large-bodied creatures. The giant millipedes, dragonflies, and other enormous arthropods that had been the dominant land animals for millions of years found themselves struggling to survive in the new lower oxygen environment. Many species went extinct entirely, while others evolved to become much smaller than their Carboniferous ancestors. At the same time, temperatures began to drop as the formation of Pangaea altered global weather patterns. The tropical conditions that had characterized much of the Carboniferous gave way to cooler, more arid climates that were hostile to many of the species that had evolved during the earlier period. But while the changing conditions were devastating for many forms of life, they created new opportunities for others. The amniotes that had evolved the ability to lay shelled eggs were perfectly adapted to survive in the drier conditions of the New World. Their scaly skin helped prevent water loss, and their reproductive independence from aquatic environments meant they could thrive in areas where amphibians couldn't survive. As the Carboniferous period came to an end around 299 million years ago, the world had been transformed once again. The age of giant arthropods was over. The great forests had given way to more arid landscapes, and the stage was set for amniotes to begin their conquest of the terrestrial world. The Permian period that followed would see the rise of the first great reptilian predators, the evolution of the ancestors of both mammals and dinosaurs, and ultimately the most devastating mass extinction in Earth's history. But that's a story that would unfold over the next 50 million years as life continued its endless struggle to adapt and survive in an ever-changing world. The transformation from the lush, oxygen-rich forests of the Carboniferous to the harsh, arid landscapes of the early Permian was like watching Earth reinvent itself from scratch. The planet that emerged from this transition was a fundamentally different place, one where the rules of survival had been completely rewritten, and where entirely new types of creatures would rise to prominence. The Permian period dawned around 299 million years ago, like Earth's own version of a desert survival reality show. Except this one lasted for 50 million years, and the contestants were every living thing of the planet. The lush, swampy paradise of the Carboniferous had been replaced by something that looked more like a post-apocalyptic wasteland, with vast stretches of arid land broken only by the occasional oasis of life. The supercontinent Pangaea was now fully formed, stretching from pole to pole like a massive landmass that had swallowed up all the smaller continents. The interior of this enormous continent was a hellscape of deserts and badland, where temperatures could soar to levels that would make modern deserts seem comfortable. The coastal areas offered some relief, but even these were much drier and harsher than the tropical paradises that had existed during the Carboniferous. But here's the fascinating thing about life. It doesn't just give up when conditions get tough. Instead, it finds new ways to not just survive, but to thrive in environments that would seem impossible to colonize. The creatures that emerged as the dominant land animals during the Permian were perfectly adapted to this harsh new world, and they were about to write one of the most remarkable chapters in the story of vertebrate evolution. The real winners in this transformed world were the amniotes, those revolutionary vertebrates that had learned to lay shelled eggs. With their scaly skin that prevented water loss and their independence from aquatic environments for reproduction, they were like biological tanks designed specifically for conquering dry land. And conquer it they did, spreading across Pangaea and diversifying into forms that would have seemed impossible just a few million years earlier. The amniotes split into two major groups that would define the future of vertebrate evolution. The first group, called synapsids, would eventually give rise to mammals, though they were still millions of years away from becoming the furry, warm-blooded creatures we know today. The second group, called sauropsids, would evolve into reptiles and eventually birds, becoming the ancestors of some of the most successful vertebrates our planet has ever seen. But it was the synapsids that truly ruled the early Permian world. These creatures had evolved from amphibian ancestors, but they had taken vertebrate design in entirely new directions. They had developed more efficient respiratory systems, better temperature regulation, and more sophisticated nervous systems that allowed them to exploit ecological niches that had never been occupied before. The undisputed champion of the early Permian was a creature called Dimetrodon, and if you've ever seen a picture of it, you might have mistaken it for a dinosaur. This massive predator had a distinctive sail-like structure on its back that made it instantly recognizable, and at up to 4.5 meters in length, it was roughly the size of a small car. But despite its reptilian appearance, Dimetrodon was actually more closely related to mammals than to any modern reptile. Dimetrodon was the apex predator of its time, a role it maintained for an impressive 16 million years. Its powerful jaws were filled with different types of teeth: sharp fangs for killing prey, cutting teeth for slicing meat, and grinding teeth for processing food. This dental diversity was a sign of the increasingly sophisticated feeding strategies that were evolving among early synapsids. The famous sail on Dimetrodon's back has been the subject of considerable scientific debate. Some researchers believe it functioned as a thermoregulatory device, helping the animal absorb heat from the sun in the morning and dissipate excess heat during the hottest parts of the day. Others suggest it may have been used for display purposes, helping individuals recognize members of their own species or intimidate rivals and potential mates. Whatever its function, the sail certainly made Dimetrodon one of the most distinctive predators of the Permian period. It stalked through the arid landscapes of Pangaea like a living sailboat, its massive frame casting long shadows across the desert floor as it hunted for prey among the scattered vegetation and rocky outcrops. But Dimetrodon wasn't the only impressive synapsid roaming the Permian landscape. As the period progressed, these creatures diversified into an incredible array of forms, from small, quick-moving insectivores to massive, slow-moving herbivores that could rival modern elephants in size. They were experimenting with different body plans, different feeding strategies, and different ways of surviving in the challenging environments of Pangaea. Eventually, Dimetrodon's reign came to an end, and its place as the dominant predator was taken by a group of synapsids called Gorgonopsians. These creatures were smaller than Dimetrodon, but arguably more dangerous, with massive saber-like teeth that could slice through the toughest hide. The largest Gorgonopsians, like Inostrancevia, could reach 3 meters in length and possessed fangs that were 15 centimeters long. Gorgonopsians were the first truly efficient mammalian predators, with body plans that were optimized for hunting and killing. They had powerful leg muscles that could propel them at high speeds, sophisticated sensory organs that could track prey over long distances, and those incredible saber teeth that could deliver devastating, killing blows to their victims. These fearsome predators shared their world with equally impressive herbivores. The sauropsids, not to be outdone by their synapsid cousins, had evolved their own giants. Creatures like Scutosaurus were massive, heavily armored plant eaters that looked like living tanks. They had thick, bony plates covering their bodies, powerful legs that could support their enormous weight, and specialized teeth for processing tough plant material. Scutosaurus and its relatives were the biological equivalent of armored personnel carriers, slow-moving but virtually indestructible. They could reach lengths of several meters and weights of several tons, making them some of the largest land animals of their time. Their armor was so effective that even the most powerful predators would have had difficulty penetrating their defenses. But perhaps the most remarkable creature of the Permian period was something called Coryphodon, a synapsid that grew to absolutely massive proportions. This creature was the largest land animal that had ever existed up to that point in Earth's history, reaching lengths that would have dwarfed even the mighty Dimetrodon. It was a gentle giant, feeding on plants and using its enormous size as protection against predators. The diversity of life during the Permian was truly staggering. The landscapes of Pangaea were home to creatures that ranged from tiny, shrew-like synapsids to massive, rhinoceros-sized herbivores. There were predators with saber teeth, herbivores with armor plating, and countless smaller creatures that filled every conceivable ecological niche. But as remarkable as this diversity was, it was built on increasingly shaky foundations. The formation of Pangaea had created a climate that was becoming progressively more extreme as the period wore on. The interior of the supercontinent was heating up, creating vast deserts that stretched for thousands of kilometers. The few remaining forests were under constant stress from drought and heat. The situation was about to get much worse. Around 252 million years ago, a series of catastrophic events began to unfold that would bring the Permian period to a devastating conclusion. It started with massive volcanic eruptions in what is now Siberia, eruptions so enormous that they would make any modern volcanic disaster look like a minor hiccup. These weren't ordinary eruptions. They were flood basalts, volcanic events that released incredible amounts of lava across areas the size of entire countries. The Siberian traps, as they're known today, covered an area roughly half the size of the United States with molten rock. The eruptions continued for thousands of years, pumping enormous quantities of toxic gases into the atmosphere. The volcanic gases included massive amounts of carbon dioxide, which began to trap heat in the atmosphere and drive global temperatures to levels that were lethal to most forms of life. The planet was experiencing what scientists call runaway greenhouse warming, where rising temperatures triggered feedback loops that caused even more warming. But the carbon dioxide wasn't the only problem. The eruptions also released huge amounts of sulfur dioxide, which reacted with water vapor in the atmosphere to create acid rain that was so corrosive it could dissolve limestone. The oceans began to absorb some of this carbon dioxide, causing seawater to become increasingly acidic, a process that was devastating to marine organisms with calcium carbonate shells. As temperatures continued to rise, the remaining forests began to catch fire. Massive wildfires swept across the continents, burning away what little vegetation remained and releasing even more carbon dioxide into the atmosphere. The planet was caught in a vicious cycle where each disaster triggered additional disasters, creating a cascade of environmental destruction that seemed unstoppable. The rising temperatures also had devastating effects on the oceans. Warmer water holds less dissolved oxygen, so as ocean temperatures rose, the amount of oxygen available to marine life decreased dramatically. This created vast dead zones where nothing could survive, turning large areas of the ocean into biological deserts. On land, the situation was equally catastrophic. The extreme heat made it impossible for most plants to survive, which in turn eliminated the food sources that herbivorous animals depended on. Without herbivores, the predators that fed on them also began to disappear. The complex food webs that had taken millions of years to develop were collapsing within a few thousand years. The marine environment was hit even harder than the terrestrial one. The combination of rising temperatures, increasing acidity, and decreasing oxygen levels created conditions that were lethal to most marine organisms. Coral reefs, which had been important centers of marine biodiversity, were among the first casualties. The creatures that built these reefs simply couldn't survive in the new chemical conditions of the oceans. The effects cascaded throughout the marine ecosystem. The tiny organisms that formed the base of the food web began to disappear, which eliminated the food sources for larger creatures. Fish populations crashed, marine reptiles went extinct, and the diverse communities of invertebrates that had populated the seafloor for millions of years simply vanished. By the time the crisis reached its peak, around 251 million years ago, the devastation was almost complete. An estimated 90% of all marine species had gone extinct, along with 70% of terrestrial vertebrates. It was the most severe mass extinction in Earth's history, an event so devastating that scientists have given it a special name: the Great Dying. The Great Dying was like hitting the reset button on life itself. Entire groups of organisms that had been dominant for millions of years simply disappeared from the fossil record, never to be seen again. The Gorgonopsians with their impressive saber teeth, the massive herbivores with their armor plating, the diverse communities of marine invertebrates, all of them vanished in what was essentially a geological instant. The few creatures that managed to survive found themselves in a world that was almost empty of life. The complex ecosystems that had taken hundreds of millions of years to develop had been reduced to a handful of hardy species clinging to existence in the most marginal environments. It was as if someone had taken a thriving city and reduced it to a ghost town, with only a few scattered survivors wandering through the ruins. But here's the remarkable thing about life. Even in the face of such overwhelming catastrophe, it doesn't give up. Those few surviving species, scattered and reduced though they were, carried within them the genetic potential for all the incredible diversity that would follow. They were the seeds from which the next great chapter of Earth's story would grow. The Permian period officially ended with the Great Dying, but its conclusion also marked the beginning of something new. The Mesozoic era was about to begin, and with it would come a completely different approach to life on Earth. The age of mammal-like reptiles was over. But the age of true reptiles was just beginning. The survivors of the Great Dying would give rise to new forms of life that would exploit the empty ecological niches left behind by the extinction. Marine reptiles would evolve to fill the roles once occupied by the vanished marine invertebrates. On land, new types of reptiles would develop that would eventually give rise to the most famous group of animals in Earth's history, the dinosaurs. But that transformation would take time. The Triassic period that followed the Great Dying began quietly, with life slowly recovering from the most devastating extinction event our planet had ever experienced. It would take millions of years for ecosystems to rebuild, for new evolutionary experiments to begin, and for the stage to be set for the next great act in the drama of life on Earth. The early Triassic was a time of rebuilding, a period when the survivors of the Great Dying had to figure out how to live in a world that had been fundamentally transformed. The climate was still harsh, the ecosystems were still broken, and the future was still uncertain. But life had survived, and where there is life, there is hope for recovery, adaptation, and eventual triumph. The Triassic period stumbled into existence around 251 million years ago, like a survivor crawling out of the wreckage of the world's worst natural disaster. The planet that emerged from the Great Dying was a shadow of its former self, a world where the few remaining creatures had inherited a landscape that was both opportunity and challenge, rolled into one devastatingly empty package. For the first 5 million years of the Triassic, life moved with the caution of someone walking through a minefield. The survivors of the Great Dying were spread thin across the continents, occupying a world that had far more available space than there were creatures to fill it. It was like having an entire shopping mall with only a handful of stores still open. Lots of potential, but it would take time to figure out how to use it. The early Triassic world was still dominated by the environmental extremes that had caused the Great Dying in the first place. Temperatures remained dangerously high, the climate was intensely arid, and the atmospheric chemistry was still recovering from the massive volcanic eruptions that had triggered the extinction. Only the hardiest, most adaptable creatures could survive in these conditions, and they were about to inherit the Earth. The synapsids, those mammal-like reptiles that had dominated the Permian, had been devastated by the extinction. Most of the impressive predators and herbivores that had characterized the late Permian were gone forever. A few small synapsid species managed to survive, and they would eventually evolve into the first true mammals. But their time as the dominant land animals was over. The future belonged to the sauropsids, the reptilian branch of the amniota family tree. These creatures had several advantages that made them particularly well suited to the harsh conditions of the post-extinction world. Their scaly skin was excellent at preventing water loss. Their shelled eggs could develop in dry environments, and their metabolism was efficient enough to function in the nutrient-poor ecosystems of the early Triassic. As the Triassic progressed, the sauropsids began to diversify and spread into ecological niches that had been vacated by the extinction. Some of them moved into the oceans, evolving into the first marine reptiles since the Great Dying. Others remained on land, developing into increasingly sophisticated forms that would eventually give rise to the most successful group of vertebrates our planet has ever seen. The marine reptiles of the Triassic were particularly remarkable. The oceans had been devastated by the Great Dying, with most of the complex marine ecosystems simply disappearing. But nature abhors a vacuum, and the surviving sauropsids were quick to exploit the opportunities presented by these empty seas. One of the most successful groups of marine reptiles was the ichthyosaurs, creatures that looked remarkably similar to modern dolphins, despite being completely unrelated. These reptiles had evolved streamlined bodies, powerful tails, and some of the largest eyes in the animal kingdom, adaptations that made them incredibly effective marine predators. The eyes of ichthyosaurs were truly extraordinary, some reaching diameters of over 20 centimeters. These massive visual organs allowed them to hunt in the deep, dark waters of the Triassic oceans, detecting prey and predators from incredible distances. They were like living submarines, perfectly adapted for life in three-dimensional aquatic environments. Alongside the ichthyosaurs, another group of marine reptiles called plesiosaurs began to establish themselves in the recovering oceans. These creatures had a completely different approach to marine life, with long necks that could snake through the water and powerful flippers that provided precise maneuvering capabilities. They were the stealth hunters of the Triassic seas, using their extended necks to strike at prey from unexpected angles. Both ichthyosaurs and plesiosaurs would go on to dominate marine ecosystems for hundreds of millions of years, proving that the Great Dying, devastating as it was, had also created opportunities for entirely new forms of life to emerge and flourish. On land, the sauropsids were experimenting with an incredible variety of body plans and lifestyles. Some, like the strange creature called Drepanosaurus, evolved to live in trees, developing long, flexible tails and powerful claws that allowed them to move through the forest canopy like prehistoric lemurs. Drepanosaurus had a particularly unusual claw on one of its fingers that was specialized for extracting insects from tree bark and crevices. These arboreal reptiles were among the first vertebrates to successfully exploit the three-dimensional environment of forest canopies. They were pioneers, in a sense, figuring out how to live and hunt in spaces that had never been occupied by large vertebrates before. Their success would pave the way for countless other species that would eventually make their homes in the trees. But perhaps the most significant development of the Triassic was the evolution of powered flight among vertebrates. The first flying reptiles, called pterosaurs, appeared during this period, and they represented one of the most remarkable innovations in the history of life on Earth. These creatures had solved the incredibly complex engineering problem of vertebrate flight, developing wings that were both strong enough to support their weight and flexible enough to allow precise control. The early pterosaurs were small creatures, but they were marvels of biological engineering. They had hollow bones that reduced their weight without sacrificing strength. wing membranes that were supported by incredibly long finger bones, and flight muscles that were powerful enough to generate the lift needed for sustained flight. They were the first vertebrates to truly conquer the three-dimensional world of the air. Not all early experiments in pterosaur flight were successful. Some species, like Cherovipteryx, had wings attached to their hind legs rather than their front legs, a design that proved to be an evolutionary dead end. These creatures could only manage clumsy gliding flights and were eventually outcompeted by more conventional pterosaur designs. But the pterosaurs that did succeed were incredibly successful. By the end of the Triassic, they had evolved into a diverse group of flying reptiles, with wingspans ranging from a few centimeters to several meters. They had figured out how to exploit the aerial environment in ways that would have seemed impossible just a few million years earlier. While these remarkable developments were taking place in the oceans and in the air, the most significant evolution of the Triassic was happening on land. With the synapsids largely eliminated by the Great Dying, the sauropsids had evolved into a new subgroup called archosaurs, and these creatures were about to change the world forever. Archosaurs had several key advantages that made them incredibly successful in the post-extinction world. They had evolved highly efficient respiratory systems that allowed them to extract more oxygen from each breath, enabling them to remain active in the low oxygen environments that characterized the early Triassic. This respiratory efficiency would prove to be crucial for their success in the challenging conditions of the post-extinction world. But perhaps more importantly, archosaurs had evolved upright limbs that extended directly beneath their bodies, rather than sprawling out to the sides like those of more primitive reptiles. This might seem like a minor anatomical detail, but it had profound implications for their success. Reptiles with sprawling limbs, like modern lizards, move by flexing their bodies from side to side. This movement pattern forces air back and forth between their lungs rather than expelling it completely, which means they can't breathe effectively while moving. As a result, these reptiles have to stop frequently to catch their breath, limiting their activity levels and making them vulnerable to predators. Archosaurs, with their upright limbs, didn't have this problem. They could breathe normally while walking or running, which gave them a tremendous advantage in both hunting and escaping from predators. They could maintain high activity levels for extended periods, allowing them to exploit ecological niches that were inaccessible to their more primitive relatives. One of the most formidable archosaurs of the Triassic was Postosuchus, a creature that looked like a terrifying cross between a crocodile and a Tyrannosaurus rex. This massive predator could reach lengths of up to 6 meters and had a skull filled with razor-sharp teeth designed for slicing through flesh and bone. It was perfectly adapted for life as an apex predator in the harsh environments of Triassic Pangaea. Postosuchus was a versatile hunter that could move on either 2 legs or 4, depending on the situation. When stalking prey, it might approach on all 4s, using its powerful limbs to move silently through the landscape. But when it was time to attack, it could rear up on its hind legs, using its massive jaws to deliver devastating bites to the neck or back of its victims. The success of archosaurs like Postosuchus meant that when the first dinosaurs appeared in the Middle Triassic, they were entering a world that was already dominated by sophisticated predators. These early dinosaurs were small, relatively unremarkable creatures that didn't immediately stand out from the crowd of other archosaurs sharing their environment. But the dinosaurs had one crucial advantage that would eventually make them the most successful group of land animals in Earth's history. They reproduced incredibly quickly compared to their archosaur relatives. While other archosaurs were producing small numbers of offspring that took years to mature, dinosaurs could produce large numbers of young that reached reproductive age relatively quickly. This rapid reproduction rate meant that dinosaurs could evolve and adapt to changing conditions much faster than their competitors. When environmental changes occurred, dinosaur populations could adjust within a few generations, while other archosaurs might take hundreds of generations to respond to the same challenges. The first dinosaurs were bipedal creatures that looked somewhat like small, agile crocodiles running on their hind legs. They had long tails for balance, powerful leg muscles for running, and sharp teeth for catching prey. They weren't particularly large or impressive compared to giants like Postosuchus, but they were perfectly designed for survival in a rapidly changing world. As the Triassic period progressed, these early dinosaurs began to diversify and spread across Pangaea. Some remained small and agile, developing into the ancestors of predatory dinosaurs. Others grew larger and began experimenting with plant-eating lifestyles, becoming the ancestors of the massive herbivorous dinosaurs that would dominate later periods. The stage was set for one of the most remarkable evolutionary experiments in Earth's history. The archosaurs had conquered the post-extinction world. The pterosaurs had mastered flight. The marine reptiles had repopulated the oceans, and the first dinosaurs had begun their journey toward global dominance. But all of this progress was about to be tested once again. The late Triassic world was becoming increasingly unstable, with climate changes and environmental pressures that would trigger another mass extinction event. This extinction would eliminate many of the archosaurs that had dominated the early Triassic, but it would also create the conditions that would allow dinosaurs to finally step out of the shadows and begin their rise to supremacy. The Triassic-Jurassic extinction event was smaller than the Great Dying, but it was perfectly timed to reshape the balance of power among land animals. The large archosaur predators like Postosuchus would disappear, along with many other groups that had been successful during the Triassic. But the dinosaurs, with their rapid reproduction and adaptability, would survive and thrive in the post-extinction world. As the Triassic period drew to a close around 201 million years ago, the stage was finally set for the age of dinosaurs to begin. The long journey from the first simple cells in ancient oceans to the rise of the most famous group of animals in Earth's history was nearly complete. The age of reptiles was about to reach its most spectacular chapter, and the world would never be the same again. The Jurassic period burst onto the scene around 201 million years ago, like nature's own grand reopening after extensive renovations. The Triassic-Jurassic extinction had just swept through the planet, eliminating many of the large archosaur predators that had dominated the post-Great Dying world. But rather than being another devastating catastrophe, this extinction event was more like a changing of the guard, one that would finally allow dinosaurs to step out of the shadows and claim their rightful place as the rulers of Earth. Picture the world as it emerged from this transition. The climate was warming significantly, transforming the arid landscapes of the late Triassic into something much more hospitable. The supercontinent Pangaea was beginning to break apart, creating new coastlines and inland seas that would moderate the extreme temperatures that had characterized the previous period. For the first time in millions of years, the planet was becoming a genuinely pleasant place to live. The breakup of Pangaea was like watching a massive jigsaw puzzle slowly coming apart. The Atlantic Ocean was beginning to form as North America and Europe started drifting away from each other. New mountain ranges were rising as the continents shifted and collided. Volcanic activity was creating new islands and reshaping existing coastlines. The entire geography of the planet was being rewritten, but the most remarkable change was in the climate itself. The Jurassic was characterized by what scientists call a greenhouse climate. Warm, humid conditions that extended from the equator almost to the poles. There were no polar ice caps, no frozen tundra, no desert wastelands stretching for thousands of kilometers. Instead, the world was covered in lush vegetation, from tropical forests near the equator to temperate woodlands in what would today be considered Arctic regions. This warm, humid climate was perfect for plant growth, and the Jurassic world exploded with vegetation in ways that would have seemed impossible during the harsh conditions of the Triassic. Vast forests of conifers spread across the continents, their towering canopies, creating complex three-dimensional ecosystems that could support incredible diversity of life. Ferns carpeted the forest floors, while primitive flowering plants began their first tentative experiments with colorful blooms. The abundance of plant life created opportunities for herbivorous animals that simply hadn't existed before. For the first time since the Great Dying, there was enough vegetation to support large populations of plant-eating creatures, and the dinosaurs, with their rapid reproduction rates and adaptability, were perfectly positioned to take advantage of these new opportunities. The early Jurassic saw the emergence of the first truly large dinosaurs. These weren't the mind-boggling giants that would appear later in the period, but they were certainly impressive by any previous standards. Creatures like Dilophosaurus prowled through the forest, standing nearly 3 meters tall and stretching over 6 meters in length. With their distinctive double crests and powerful jaws filled with sharp teeth, they were formidable predators that could take down prey much larger than themselves. But Dilophosaurus wasn't just big, it was also remarkably sophisticated. Recent studies of its fossils have revealed that it had complex nasal passages that may have been used for making sounds, sophisticated sensory organs for tracking prey, and a brain that was much more advanced than those of its archosaur predecessors. It was a predator that could think, plan and adapt in ways that would have been impossible for earlier reptiles. The success of predators like Dilophosaurus created evolutionary pressure for herbivorous dinosaurs to develop new defensive strategies. Some responded by growing larger, reasoning that size alone might deter potential predators. Others developed armor plating, spikes, or other physical defenses. Still others evolved to live in herds, using group behavior to detect and respond to threats. One of the most remarkable herbivorous dinosaurs of the early Jurassic was Plateosaurus, a creature that pioneered the long-necked, plant-eating lifestyle that would become so characteristic of later dinosaur faunas. At up to 10 meters in length, Plateosaurus was enormous by the standards of its time, but it was also remarkably graceful, capable of rearing up on its hind legs to reach vegetation that was inaccessible to other herbivores. Plateosaurus represented a completely new approach to herbivory. Unlike the sprawling, low-slung plant eaters of previous periods, these dinosaurs were tall, elegant creatures that could browse on vegetation at multiple levels of the forest canopy. They were like living giraffes, using their long necks to access food sources that were beyond the reach of their competitors. The success of these early herbivorous dinosaurs set the stage for an evolutionary arms race that would define the rest of the Mesozoic era. As herbivores grew larger and more numerous, predators had to evolve new strategies for hunting them. As predators became more sophisticated, herbivores had to develop better defenses. This constant pressure for innovation drove both groups to evolve in increasingly spectacular directions. But dinosaurs weren't the only reptiles making impressive evolutionary strides during the Jurassic. The marine reptiles that had first appeared during the Triassic were reaching new heights of sophistication and diversity. The oceans of the Jurassic were dominated by creatures that would have made the most fearsome modern marine predators look like minnows. The ichthyosaurs had evolved into some of the most perfectly adapted marine predators our planet has ever seen. Creatures like Ophthalmosaurus had streamlined bodies that could cut through the water with incredible efficiency, powerful tails that could propel them at speeds rivaling those of modern dolphins, and those characteristic enormous eyes that could detect prey in the deepest, darkest waters. But perhaps the most impressive marine reptile of the Jurassic was Leadsichthys, a creature so enormous that it challenges our understanding of what's possible for a marine vertebrate. This massive fish, yes, it was actually a fish, not a reptile, could reach lengths of over 16 meters, making it one of the largest bony fish that has ever lived. It was a filter feeder, using its massive mouth to strain plankton and small fish from the water like a prehistoric whale. The presence of creatures like Leadsichthys in Jurassic oceans tells us something important about the productivity of marine ecosystems during this period. For such a massive filter feeder to evolve and thrive, the oceans must have been incredibly rich in small organisms. The warm, nutrient-rich seas of the Jurassic were supporting food webs of incredible complexity and abundance. Plesiosaurs were also reaching new levels of diversity and specialization during the Jurassic. Some, like Cryptoclydus, had incredibly long necks that could snake through the water with serpentine grace, allowing them to strike at prey from unexpected angles. others, like the massive Leopleurodon, had evolved into apex predators with skulls over 2 meters long and teeth that could crush virtually any prey. Leopleurodon was particularly impressive, a creature that combined the stealth of a crocodile with the power of a great white shark. Its massive skull was filled with teeth that were perfectly designed for gripping and crushing, while its powerful flippers could propel its enormous body through the water with surprising speed. It was the undisputed ruler of the Jurassic seas, a predator that could take down virtually any other marine creature. The success of these marine reptiles was creating complex oceanic ecosystems that rivaled anything in the modern world. The Jurassic seas were filled with predators and prey at every level, from tiny plankton to massive filter feeders, from agile fish to enormous marine reptiles. It was a three-dimensional world of incredible complexity and beauty. Meanwhile, in the skies above, the pterosaurs were continuing their own remarkable evolutionary journey. The early Jurassic saw the emergence of pterosaurs that were larger and more sophisticated than their Triassic predecessors. Creatures like Dimorphodon had wingspans approaching 1.5 meters and were capable of both powered flight and precise maneuvering through forest canopies. But perhaps more importantly, pterosaurs were beginning to diversify into different ecological niches. Some were becoming specialized fish eaters, developing long, narrow beaks, perfect for snatching prey from the water's surface. Others were evolving into aerial insectivores, using their agility and speed to catch flying insects. Still others were experimenting with plant-eating lifestyles, becoming the first vertebrates to combine flight with herbivory. The diversity of pterosaurs during the Jurassic was truly remarkable. They ranged from tiny, sparrow-sized creatures that flitted through the forest understory to larger, more powerful forms that could soar over vast distances. They were filling ecological niches that had never been occupied before, creating entirely new ways of living in the three-dimensional world of the air. Back on land, the dinosaurs were entering what could only be described as their golden age. The Middle and Late Jurassic saw the emergence of some of the most spectacular dinosaurs that ever lived, creatures that would capture the imagination of people for generations to come. The world was about to meet its first true giants. The late Jurassic was dominated by the sauropods, those incredible long-necked herbivores that represent the pinnacle of dinosaur evolution in terms of sheer size. Creatures like Brachiosaurus, Diplodocus, and Apatosaurus were unlike anything that had ever walked the earth before. They were living skyscrapers, animals so large that they seemed to defy the laws of physics. Brachiosaurus was perhaps the most impressive of these giants, standing over 13 meters tall and weighing as much as 12 elephants. Its long neck allowed it to browse on vegetation that was completely inaccessible to other herbivores, while its massive body provided protection from all but the most determined predators. It was like a living giraffe, scaled up to proportions that would have seemed impossible. But Brachiosaurus wasn't just big. It was also remarkably efficient. Its long neck was supported by an intricate system of air-filled bones that reduced its weight without sacrificing strength. Its massive heart was capable of pumping blood all the way up to its head, despite the enormous distance involved. Its digestive system was perfectly adapted for processing huge quantities of plant material, allowing it to extract maximum nutrition from relatively low-quality vegetation. The success of sauropods like Brachiosaurus created new opportunities for predators, but it also presented them with unprecedented challenges. How do you hunt an animal that weighs as much as a small building? The answer came in the form of predators that were themselves giants, creatures that combined size with intelligence and sophisticated hunting strategies. Allosaurus was the apex predator of the late Jurassic, a creature that perfectly embodied the evolutionary arms race between predator and prey. At up to 12 meters in length and weighing several tons, it was large enough to pose a serious threat to even the biggest sauropods. Its powerful jaws were filled with serrated teeth that could slice through flesh and bone with ease, while its strong legs could propel it at speeds that would have been surprising for such a large animal. But Allosaurus wasn't just a mindless killing machine. It was an intelligent predator that used sophisticated hunting strategies. Evidence suggests that these dinosaurs may have hunted in coordinated groups using teamwork to bring down prey that would have been impossible for a single individual to handle. They were the wolves of the dinosaur world, combining individual power with collective intelligence. The late Jurassic also saw the emergence of some of the most heavily armored dinosaurs that ever lived. Stegosaurus, with its distinctive rows of plates along its back and its spiked tail, was a walking fortress designed to deter predators through a combination of intimidation and genuine defensive capability. The spikes on its tail, nicknamed thagomizers by paleontologists, were capable of inflicting serious wounds on any predator foolish enough to attack from behind. But Stegosaurus wasn't just defensive, it was also remarkably sophisticated. Recent studies have suggested that the plates along its back may have been used for thermoregulation, helping the animal maintain optimal body temperature in the warm climate of the Jurassic. They may also have been used for display purposes, helping individuals recognize members of their own species or communicate with potential mates. The diversity of dinosaurs during the late Jurassic was truly staggering. There were tiny bird-like predators that hunted insects and small vertebrates. There were massive herbivores that could strip entire forests of vegetation. There were armored tanks that could withstand attacks from the most powerful predators. There were aerial acrobats that could glide from tree to tree. The dinosaurs had successfully colonized virtually every terrestrial ecological niche. But perhaps the most significant development of the late Jurassic was one that wouldn't be fully appreciated until much later: the evolution of the first birds. Archaeopteryx, discovered in the limestone quarries of Germany, was a creature that perfectly bridged the gap between dinosaurs and modern birds. It had feathers, wings, and the ability to fly, but it also had teeth, claws, and a long, bony tail like its dinosaur ancestors. Archaeopteryx was proof that birds were not just related to dinosaurs. They were dinosaurs, a specialized group that had evolved the ability to fly. This revolutionary creature was opening up entirely new possibilities for vertebrate evolution, possibilities that would eventually lead to the incredible diversity of birds we see today. The late Jurassic world was reaching levels of biological complexity and diversity that were unprecedented in Earth's history. The continents were covered in lush forests filled with dinosaurs of every conceivable size and shape. The oceans teemed with marine reptiles that had evolved to exploit every possible ecological niche. The skies were filled with pterosaurs and the first primitive birds, creatures that had finally mastered the three-dimensional world of flight. But this golden age was not destined to last forever. The Jurassic period was coming to an end, and with it would come new challenges and opportunities that would reshape the biological landscape once again. The Cretaceous period that followed would see the rise of flowering plants, the evolution of even more spectacular dinosaurs, and ultimately the catastrophic extinction that would bring the age of dinosaurs to a dramatic close. As the Jurassic period drew to a close around 145 million years ago, the world was poised on the brink of another great transformation. The stage was set for the final act of the Mesozoic era, a period that would see life on Earth reach new heights of complexity and diversity before facing its greatest challenge yet. The transition from the Jurassic to the Cretaceous was like watching the Earth graduate from impressive to absolutely mind-blowing. Around 145 million years ago, our planet was about to embark on the final chapter of the Mesozoic era, a period that would push the boundaries of what was possible for life on Earth in ways that still leave scientists speechless today. The early Cretaceous world was a place of dramatic change and unprecedented opportunity. The supercontinent Pangaea was continuing to break apart, creating new ocean basins and completely reshaping the planet's geography. The Atlantic Ocean was widening, separating the Americas from Europe and Africa. New mountain ranges were rising as the continents shifted and collided. Volcanic islands were emerging from the depths of the oceans, creating entirely new environments for life to colonize. But perhaps the most significant change was happening in the plant kingdom. The Cretaceous would witness one of the most important evolutionary innovations in the history of life on Earth. The rise of flowering plants, or angiosperms. These weren't just another type of plant. They were a complete revolution in how plants reproduced, survived, and interacted with the animals around them. The first flowering plants appeared in the early Cretaceous, like botanical pioneers, experimenting with entirely new strategies for reproduction and survival. Unlike the conifers and ferns that had dominated previous periods, these plants had evolved colorful flowers that could attract insects and other animals to help with pollination. They had developed fruits that could entice animals to eat them and disperse their seeds across vast distances. They had created a partnership with the animal kingdom that would prove to be one of the most successful collaborations in the history of life. The impact of flowering plants on terrestrial ecosystems was absolutely revolutionary. Within a few million years, they had spread across the continents, creating entirely new types of habitats and food webs. The forests of the Cretaceous were no longer the monotonous green landscapes of earlier periods. They were vibrant, colorful environments filled with an incredible diversity of plant species. This botanical revolution created new opportunities for herbivorous dinosaurs, that were unlike anything that had existed before. The flowering plants were producing fruits, nuts, and other high-energy food sources that were much more nutritious than the tough, fibrous vegetation that had characterized earlier periods. Herbivorous dinosaurs could now access concentrated sources of energy that allowed them to grow larger and more active than ever before. The response of dinosaurs to this new world of abundance was spectacular. The Cretaceous saw the evolution of some of the most impressive herbivorous dinosaurs that ever lived, creatures that took the sauropod body plan and pushed it to its absolute limits. Argentinosaurus, discovered in South America, may have been the largest land animal that ever lived, reaching lengths of over 30 meters and weights that could have exceeded 100 tons. Imagine trying to comprehend the sheer scale of Argentinosaurus. This creature was longer than 3 school buses placed end to end, taller than a 4-story building, and so heavy that its footsteps would have shaken the ground for kilometers around. It was a living mountain, a creature so large that it seems to challenge our understanding of what's physically possible for a terrestrial animal. But Argentinosaurus wasn't just big, it was also remarkably sophisticated. Its skeleton was a masterpiece of biological engineering, with hollow bones that reduced weight without sacrificing strength, and a complex system of air sacs that helped it breathe efficiently despite its enormous size. Its heart was the size of a small car, capable of pumping blood throughout its massive body. Its digestive system was like a biological processing plant, capable of extracting nutrients from hundreds of kilograms of plant material every day. The existence of giants like Argentinosaurus created new challenges for predators, but it also created new opportunities. The Cretaceous saw the evolution of predatory dinosaurs that were themselves giants, creatures that combined size with intelligence and sophisticated hunting strategies in ways that were unprecedented in Earth's history. Giganotosaurus was perhaps the most impressive of these super predators, a creature that may have been even larger than the famous Tyrannosaurus rex. At over 13 meters in length and weighing as much as 8 tons, it was perfectly adapted for hunting the massive sauropods that dominated Cretaceous ecosystems. Its skull was over 1.5 meters long, filled with serrated teeth that could slice through flesh and bone with devastating efficiency. But Giganotosaurus wasn't just a scaled-up version of earlier predators. It was a completely new type of hunter. Evidence suggests that these massive predators may have hunted in coordinated groups, using complex social behaviors to bring down prey that would have been impossible for a single individual to handle. They were intelligent, social creatures that used teamwork and strategy to overcome prey that was many times their own size. The arms race between predator and prey during the Cretaceous led to the evolution of some of the most heavily armored dinosaurs that ever lived. Ankylosaurus was like a living tank, covered from head to tail in thick, bony plates that could deflect the attacks of even the most powerful predators. Its tail ended in a massive club that could deliver devastating blows to any creature foolish enough to attack from behind. But perhaps even more impressive was Triceratops, a creature that combined defensive armor with offensive weapons in ways that were truly spectacular. Its massive skull, which could reach lengths of over 2 meters, was dominated by 3 enormous horns that could inflict serious damage on any predator. Its bony frill not only provided protection for its neck, but also served as a display structure that could communicate with other members of its species. The diversity of dinosaurs during the Cretaceous was truly staggering. There were tiny bird-like predators that hunted insects and small vertebrates. There were massive herbivora that could strip entire forests of vegetation. There were armored tanks that could withstand attacks from the most powerful predators. There were duck-billed dinosaurs that lived in massive herds and communicated through complex vocalizations. The dinosaurs had successfully colonized virtually every terrestrial ecological niche and had evolved solutions to every conceivable survival challenge. But the Cretaceous wasn't just about dinosaurs. It was also a time of incredible innovation and diversity among other groups of organisms. The marine reptiles that had first appeared in the Triassic were reaching new heights of sophistication and specialization. The oceans of the Cretaceous were dominated by creatures that would have made the most fearsome modern marine predators look like harmless pets. Mosasaurus was perhaps the most impressive of these marine giants, a creature that combined the stealth of a crocodile with the power of a great white shark and the size of a sperm whale. These massive marine lizards could reach lengths of over 17 meters and possessed skulls that were over 1.5 meters long, filled with teeth that could crush virtually any prey. The pterosaurs of the Cretaceous were also reaching unprecedented sizes and levels of specialization. Quetzalcoatlus, with its wingspan of over 10 meters, was one of the largest flying creatures that ever lived. It was like a prehistoric airplane, capable of soaring over vast distances and landing with the precision of a modern aircraft. Its massive size allowed it to exploit ecological niches that were inaccessible to smaller flying creatures. But perhaps the most significant development of the Cretaceous was the continued evolution of birds. The primitive Archaeopteryx of the Jurassic had given rise to an incredible diversity of bird species that were beginning to compete with pterosaurs for control of the skies. These early birds were developing increasingly sophisticated flight capabilities, complex social behaviors, and specialized feeding strategies that would eventually make them one of the most successful groups of vertebrates on Earth. The Cretaceous world was reaching levels of biological complexity and diversity that were unprecedented in Earth's history. The continents were covered in flowering plant communities of incredible richness and beauty. The oceans teemed with marine reptiles that had evolved to exploit every possible ecological niche. The skies were filled with pterosaurs and birds that had mastered the three-dimensional world of flight. The terrestrial environments were dominated by dinosaurs of every conceivable size and shape, from tiny feathered predators to massive long-necked herbivores. But this incredible diversity and abundance was about to face its greatest challenge yet. Around 66 million years ago, a catastrophe of unimaginable proportions was about to strike the Earth, an event that would bring the age of dinosaurs to a dramatic and sudden end. The impact of a massive asteroid would trigger a chain of events that would eliminate 3/4 of all species on Earth, including virtually all of the non-avian dinosaurs. The Cretaceous-Paleogene extinction event was like hitting the reset button on evolution itself. The complex ecosystems that had taken millions of years to develop were destroyed in a matter of months. The giant dinosaurs that had dominated terrestrial environments for over 160 million years simply vanished from the fossil record. The marine reptiles that had ruled the oceans for equally long periods disappeared without a trace. But from this catastrophic ending would come new beginnings. The few groups of organisms that managed to survive the extinction, including birds, mammals, and many types of plants, would inherit a world that was suddenly full of empty ecological niches. They would rapidly diversify and evolve to fill the roles that had been vacated by the extinct dinosaurs and marine reptiles. The mammals, which had spent the entire Mesozoic era as small nocturnal creatures living in the shadows of the dinosaurs, would finally have their chance to shine. They would evolve into the incredible diversity of forms we see today, from tiny shrews to massive whales, from underground moles to aerial bats. They would eventually give rise to primates and ultimately to humans, the species that would one day uncover the fossilized remains of the dinosaurs and piece together the incredible story of life before their time. The birds, as the only surviving dinosaurs, would carry the legacy of their ancient lineage into the modern world. They would evolve into thousands of species, conquering virtually every environment on Earth and proving that the dinosaur lineage was far from extinct. It had simply transformed into something new and equally remarkable. And so our journey through the incredible world of life before dinosaurs comes to its conclusion. We have traveled through billions of years of Earth's history, from the first simple cells in ancient oceans to the rise and fall of the most spectacular creatures our planet has ever seen. We have witnessed mass extinctions that brought life to the brink of annihilation, and we have seen the incredible resilience and creativity of evolution in responding to these challenges. The story of life before dinosaurs is ultimately a story of survival, adaptation, and endless experimentation. It is a testament to the incredible power of evolution to create complexity from simplicity, beauty from chaos, and hope from catastrophe. It reminds us that we are part of an unbroken chain of life that stretches back to the very beginnings of our planet, and that every creature that has ever lived has contributed to the incredible diversity of life we see today. As you drift off to sleep tonight, remember that you are the descendant of countless generations of survivors, creatures that faced unimaginable challenges and found ways to overcome them. You carry within your cells the genetic legacy of the first organisms that learned to harness the power of sunlight, the first creatures that developed the ability to see, the first animals that learned to fly, and the first mammals that survived the extinction of the dinosaurs. The story of life is far from over. Evolution continues to work its magic, creating new forms of life and new solutions to the challenges of existence. Who knows what incredible creatures might evolve in the millions of years to come? The only certainty is that life will continue to surprise us, challenge us, and inspire us with its endless creativity and resilience. Sweet dreams, and may your sleep be filled with visions of the incredible world that existed long before dinosaurs ever walked the earth. The rise of archosaurs marked a fundamental turning point in the history of life on Earth, but their story was far from over. As these remarkable creatures established themselves as the dominant land animals, they were setting the stage for one of the most important evolutionary developments our planet had ever witnessed. Within the diverse family of archosaurs, a particular group was quietly emerging that would eventually change everything. These early dinosaurs didn't announce their arrival with fanfare or dramatic displays of power. Instead, they appeared as relatively modest creatures, small and agile, moving through the landscape with a grace that set them apart from their more cumbersome relatives. The first dinosaurs were bipedal runners, built for speed and efficiency rather than brute force. Their bodies were streamlined, their limbs positioned directly beneath them for maximum locomotion efficiency. They possessed keen senses, sharp teeth, and most importantly, a reproductive strategy that would prove to be their secret weapon in the evolutionary arms race that was about to unfold. While creatures like Pastosuchus dominated through sheer size and power, these early dinosaurs were playing a completely different game. They could produce offspring faster than their competitors, allowing their populations to adapt and respond to environmental changes with unprecedented speed. This reproductive advantage would prove crucial as the Triassic world began to shift once again. The late Triassic was becoming increasingly unstable. Climate fluctuations were becoming more frequent and severe, putting pressure on all forms of life to adapt or perish. Volcanic activity was increasing, releasing gases that altered atmospheric chemistry and triggered environmental changes that cascaded through ecosystems worldwide. As these pressures mounted, the rapid generation time of dinosaurs became their greatest asset. While other archosaurs struggled to adapt to changing conditions, dinosaur populations could evolve new characteristics within just a few generations. They were like biological startups, nimble and innovative, competing against established corporations that were too large and slow to respond to market changes. The diversity of early dinosaurs was already beginning to hint at the incredible evolutionary potential of the group. Some remained small and swift, perfecting the art of hunting smaller prey with lightning-fast reflexes. Others began experimenting with larger body sizes, developing the first hints of the gigantism that would later characterize many dinosaur lineages. Still others were taking their first tentative steps toward herbivory, developing digestive systems that could process plant material more efficiently than their carnivorous ancestors. These early plant eaters were pioneers in every sense, exploring ecological niches that had been largely unexploited by previous vertebrate groups. The social behaviors of early dinosaurs were also beginning to differentiate them from their archosaur relatives. Evidence suggests that some species were developing complex group dynamics, with individuals cooperating in ways that enhanced their survival prospects. They were learning to communicate through vocalizations, body language, and possibly even primitive forms of display behavior. As the Triassic period drew toward its close, these various evolutionary experiments were creating a foundation for what would become the most successful group of large land animals in Earth's history. The stage was set for dinosaurs to inherit the Earth, but that inheritance would come at a price paid by the very creatures that had dominated the Triassic world. The end Triassic extinction event began around 201 million years ago, triggered by massive volcanic eruptions that would make even the Siberian traps look modest by comparison. The Central Atlantic Magmatic Province, as scientists call it today, released enormous quantities of lava and toxic gases across multiple continents, fundamentally altering the planet's climate and chemistry. Unlike the gradual buildup that had characterized the Great Dying, this extinction event was relatively swift and decisive. The large archosaur predators that had ruled the Triassic landscapes found themselves unable to cope with the rapidly changing conditions. Their slow reproductive rates, which had been adequate during stable periods, became a fatal liability when quick adaptation was essential for survival. Postosuchus and its relatives disappeared from the fossil record with surprising suddenness, along with many other groups that had been successful during the Triassic. The complex terrestrial ecosystems that had developed over millions of years collapsed within a few 100,000 years, leaving vast ecological voids that would need to be filled by whatever creatures managed to survive. But while this extinction was devastating for many forms of life, it created unprecedented opportunities for the survivors. The dinosaurs, with their rapid reproduction and adaptability, were perfectly positioned to exploit these opportunities. They emerged from the extinction event like entrepreneurs stepping into a market that had suddenly been cleared of all major competitors. The early Jurassic world that emerged from this transition was a fundamentally different place. The climate was warming and becoming more humid, creating conditions that were ideal for plant growth. The breakup of Pangaea was accelerating, creating new coastlines and moderating the extreme temperatures that had characterized the interior of the supercontinent. For the first time in millions of years, the continents were becoming genuinely hospitable places for large animals to live. Vast forests were spreading across the landscape, creating three-dimensional habitats that could support incredible diversity of life. Rivers and lakes were becoming more numerous and stable, providing reliable water sources for terrestrial animals. The dinosaurs wasted no time in taking advantage of these improved conditions. They began diversifying at an unprecedented rate, splitting into the two major groups that would define their future success. The Saurischian dinosaurs, with their lizard-like hip structure, would give rise to both the massive long-necked sauropods and the fearsome predatory theropods. The Ornithischian dinosaurs, with their bird-like hip arrangement, would evolve into an incredible variety of armored, horned, and duck-billed herbivores. This rapid diversification was like watching evolution in fast forward. Within just a few million years, dinosaurs had evolved solutions to virtually every conceivable survival challenge. They had developed new methods of locomotion, new feeding strategies, new defensive mechanisms, and new ways of interacting with their environment and each other. The success of dinosaurs during the Jurassic was not just about their individual adaptations, but about their ability to create and maintain complex ecosystems. They were ecosystem engineers, shaping their environments in ways that benefited not just themselves, but countless other species. Their activities created habitats for smaller animals. Their waste products fertilized plant communities, and their presence influenced the evolution of virtually every other form of life. As we reach the end of our incredible journey through the world of life before dinosaurs, we can see that their eventual rise to dominance was not inevitable, but rather the result of a perfect storm of evolutionary innovations, environmental changes, and sheer biological persistence. They inherited a world that had been shaped by billions of years of evolutionary experimentation, mass extinctions, and remarkable recoveries. The story of life before dinosaurs is ultimately a story about the power of evolution to create solutions to seemingly impossible challenges. From the first simple cells that learned to harness sunlight to the complex archosaurs that dominated the Triassic world, each chapter in this epic tale represents a breakthrough that seemed impossible when viewed from the perspective of earlier periods. The trilobites that scuttled across Cambrian seafloors, the massive sea scorpions that ruled Ordovician oceans, the first vertebrates that learned to breathe air, the plants that transformed barren continents into green landscapes, the synapsids that survived the Great Dying, and the archosaurs that rebuilt terrestrial ecosystems. All of these creatures and countless others contributed to the world that dinosaurs would inherit. Each extinction event, devastating as it was, also created opportunities for new forms of life to emerge and flourish. Each environmental challenge forced life to become more sophisticated, more resilient, and more creative in its solutions. The world that dinosaurs inherited was not a blank slate, but a planet that had been enriched by hundreds of millions of years of evolutionary innovation. As you drift off to sleep tonight, remember that you are connected to this incredible story. The oxygen you breathe was first produced by ancient cyanobacteria. The complex cells that make up your body evolved from the merger of different bacterial species billions of years ago. The backbone that supports your frame was first developed by primitive fish in Ordovician seas. The four limbs that carry you through the world were innovations of early tetrapods exploring Devonian shorelines. You are the product of an unbroken chain of survival that stretches back to the very beginnings of life on Earth. Every creature in this epic story faced challenges that seemed insurmountable, yet somehow found ways to overcome them. They passed their solutions down through the generations, creating the biological legacy that lives on in every cell of your body. The age of dinosaurs that followed this incredible prelude would itself be a remarkable chapter in the story of life, filled with giants and innovations that would capture imaginations for generations to come. But their success was built on the foundation laid by all the creatures that came before them, the pioneers and experimenters who figured out how to live, thrive, and evolve on a planet that was constantly changing. Sleep well, knowing that you carry within you the genetic wisdom of countless generations of survivors. Dream of ancient seas filled with strange and wonderful creatures, of forests where the first vertebrates learned to walk on land, of skies that knew the first experiments in powered flight. Dream of a world where life never gave up, no matter how impossible the challenges seemed. The story of life before dinosaurs is a testament to the incredible resilience and creativity of evolution. But it's also a reminder that nothing in nature is permanent. The creatures that seemed invincible in their time, from the mighty trilobites to the fearsome sea scorpions, all eventually gave way to new forms of life that were better adapted to changing conditions. Oh, as you close your eyes tonight, let your mind wander through the vast stretches of time we've explored together. Picture the early Earth, that molten ball of rock slowly cooling into something that could support the first flickering sparks of life. Imagine those first simple cells, so basic that they barely qualified as living things, yet carrying within them the potential for all the incredible diversity that would follow. Think about the patience of evolution, the way it worked for billions of years with nothing but single-celled organisms, slowly building the foundation for more complex life. Those early bacteria and archaea weren't just marking time. They were fundamentally transforming the planet, pumping oxygen into the atmosphere, creating the chemical conditions that would make complex life possible. The Cambrian explosion was like nature's own Big Bang, a burst of evolutionary creativity that produced the basic body plans for virtually all modern animal groups. In just a few million years, the oceans went from being dominated by simple, soft-bodied creatures to being filled with an incredible array of complex animals with eyes, limbs, shells, and sophisticated nervous systems. But the Cambrian was just the beginning. Each subsequent period brought new innovations, new challenges, and new solutions. The Ordovician saw the rise of the first massive predators and the first tentative steps of life onto land. The Silurian witnessed the development of the first complex terrestrial ecosystems and the evolution of jawed vertebrates. The Devonian brought us the first forests and the first vertebrates that could breathe air. The Carboniferous was a time of abundance and gigantism when oxygen levels soared and arthropods grew to sizes that would seem impossible today. The Permian saw the rise of the first truly successful land vertebrates, creatures that could thrive in the harsh conditions of the supercontinent Pangaea. And the Triassic, emerging from the devastation of the Great Dying, set the stage for the rise of the archosaurs, and ultimately the dinosaurs. Each of these periods was a complete world unto itself, with its own characteristic animals, plants, and ecosystems. Yet they were all connected by the unbroken thread of evolution, each one building on the innovations of the previous periods while adding its own unique contributions to the story of life. The mass extinctions that punctuated this history were not just endings, they were also beginnings. Each extinction event cleared away established species and ecosystems, creating opportunities for new forms of life to emerge and flourish. The survivors of these catastrophes were often the ancestors of the most successful groups in the period that followed. The Great Dying, the most severe extinction in Earth's history, eliminated 90% of marine species and 70% of terrestrial vertebrates. Yet, from this devastation emerged the archosaurs, the group that would eventually give rise to dinosaurs, pterosaurs, and crocodiles. The end Triassic extinction cleared the way for dinosaurs to become the dominant land animals of the Mesozoic era. This pattern of destruction and renewal is one of the most remarkable aspects of life's history on Earth. It shows us that even the most catastrophic events can ultimately lead to new opportunities and innovations. Life doesn't just survive these challenges, it uses them as stepping stones to even greater complexity and diversity. The world that dinosaurs inherited was not a simple place, but a planet that had been shaped by hundreds of millions of years of evolutionary experimentation. They built their success on the foundation laid by countless previous innovations. The development of complex cells, the evolution of multicellular organisms, the invention of eyes and limbs and nervous systems, the conquest of land by plants and animals, the development of efficient respiratory systems and upright posture. But dinosaurs also brought their own innovations to the table. They perfected the art of rapid reproduction and adaptation, allowing them to respond quickly to environmental changes. They developed new feeding strategies, new defensive mechanisms, and new ways of interacting with their environment. They created some of the most spectacular creatures our planet has ever seen, from the massive sauropods to the fearsome predators that hunted them. The story of dinosaurs is often told as if they appeared suddenly and dominated the earth through sheer force. But the reality is much more interesting. They were the products of a long evolutionary process, the latest chapter in a story that had been unfolding for billions of years. Their success was built on the accumulated innovations of countless previous generations of organisms. As you drift toward sleep, remember that this incredible story is not just ancient history, it's your history too. Every breath you take connects you to those early cyanobacteria that first learned to produce oxygen. Every thought you think is processed by a brain that evolved from the simple nervous systems of early animals. Every step you take is powered by muscles that trace their ancestry back to the first vertebrates that learned to move on land. You are not separate from this story. You are part of it. You carry within your cells the genetic legacy of every major evolutionary innovation we've discussed tonight. The complex chemistry that keeps you alive was perfected over billions of years by countless generations of organisms, each one contributing its own small part to the magnificent whole. The DNA in your cells contains echoes of the first genetic experiments in primordial oceans. The proteins that build your body are variations on themes that were first developed by ancient bacteria. The immune system that protects you from disease evolved from the defensive mechanisms of early multicellular organisms. The eyes that let you see the world around you are descendants of the first light-sensitive cells that appeared in Cambrian seas. This is what makes the story of life before dinosaurs so remarkable. It's not just about strange creatures from the distant past, but about the long journey that led to the emergence of consciousness itself. Every organism in this epic tale played a role in creating the conditions that would eventually allow complex brains to evolve brains capable of understanding and appreciating the very story of their own creation. The trilobites that scuttled across ancient seafloors were experimenting with the first complex visual systems. The early vertebrates that learned to breathe air were developing the respiratory systems that would eventually support large active brains. The plants that transformed the continents were creating the oxygen-rich atmosphere that would make complex thought possible. Even the mass extinctions played a crucial role in this story. By eliminating dominant species and creating new opportunities for innovation, they forced life to become more adaptable, more resilient, and ultimately more intelligent. The survivors of these catastrophes were often the ancestors of the most successful and sophisticated organisms in the periods that followed. The Great Dying, devastating as it was, cleared the way for the archosaurs that would eventually give rise to birds. The dinosaurs that survived the end Cretaceous extinction and went on to develop some of the most sophisticated behaviors in the animal kingdom. The end Triassic extinction created the conditions that allowed dinosaurs to diversify into the incredible array of forms that would dominate the Mesozoic era. This pattern of crisis and innovation is one of the most important lessons we can learn from the story of life before dinosaurs. It shows us that even the most challenging circumstances can lead to new opportunities and breakthroughs. Life doesn't just endure hardships. It transforms them into stepping stones toward greater complexity and success. As you settle into sleep tonight, let this knowledge fill you with wonder and peace. You are the product of an unbroken chain of survival that stretches back to the very beginnings of life on Earth. Every challenge that seemed insurmountable was overcome. Every extinction that seemed final was followed by new beginnings. Every innovation that seemed impossible was eventually achieved. The story of life before dinosaurs is ultimately a story of hope. It shows us that no matter how dark the present moment might seem, there is always the potential for new growth, new innovations, and new forms of beauty to emerge. The same creative force that transformed simple cells into complex organisms, that turned barren continents into lush forests, that gave rise to the first creatures capable of flight and thought, is still at work in the world today. Sweet dreams, and may your rest be filled with visions of the incredible journey that brought you into existence. Dream of ancient seas teeming with strange and wonderful creatures. Dream of the first forests where vertebrates learned to walk on land. Dream of the moment when consciousness first flickered to life in the brain of an early animal. Dream of the long, winding path that led from the first spark of life to the miracle of your own existence. You are a living testament to the power of evolution, the creativity of life, and the endless possibilities that emerge when challenges are met with persistence and innovation. Rest well, knowing that you carry within you the wisdom of billions of years of survival, adaptation, and triumph against all odds.